Welcome to the next lecture in the course Introduction to R Software. You may kindly recall that in the last lecture we had discussed some graphical tools to represent the characteristics of our data that are hidden inside it, and with the graphical tools we are trying to take them out. For example, we had discussed different types of graphics like a histogram, bar plot and so on. Now we are moving towards analytical tool, and in this lecture we are going to discuss the tools to measure the central tendency and variation of data. And you already have done most of the things in your earlier classes like as mean, median, variance, standard deviation and so on. So essentially we are going to briefly discuss these concepts, and we will try to see how they can be computed using the R software. So we start our lecture over here, and as we had discussed in the earlier lecture, whenever we get a data, the first hand information is given by two types of tool. First are analytical tool and second are graphical tool. So now under the analytical tool there can be different characteristics, and here we are going to consider the central tendency of data and the variation in data. There are different tools which are used to measure the central tendency of the data like mean, median, mode, geometric mean, harmonic mean, etc. And similarly, when we want to measure the variation in the data, there are different tools like variance, standard deviation, standard error, mean deviation, absolute deviation, etc. So first we are going to concentrate upon the different measures for the central tendency. First question comes, what is this central tendency and what do we really mean by this? So whenever we get a data, we would like to see what is the value around which they are concentrated. For example, suppose you get some values and if you try to plot them, and suppose this looks like this. So one can see here that this is the point here in the center around which all the values are concentrated. So this is trying to indicate the measure of a central tendency, right. So there are different measures of central tendency, so we discuss them one by one. So first of all, let me denote the data. This is here given by x1, x2, xn. What do we really mean by this x1, x2, xn? So let me take a simple example and try to understand what do we really mean by this thing, and the same concept will continue in the entire lecture. Suppose I want to measure the height of some persons, and suppose I measure the height of first person, and this comes out to be suppose 154 centimeters, and then I measure the height of second person which comes out to be 170 centimeters. Similarly, I consider the third person and this height comes out to be 165 centimeters, and similarly I continue. And suppose I consider here suppose 10th person, and suppose the height of 10th person comes out to be 158 centimeters. So this is indicating that we have considered here a variable x whose name is height, and then we are trying to obtain the data on this variable height. So now here is my variable x, and on which when I try to obtain the first value of the data, this is denoted here as a x1. When I try to get the second data, this is denoted as x2, and when I get the third data, this is denoted as here x3, and finally I will have here altogether 10 values, and the last value is the x10. So in this case you can see here n is equal to 10. So this x1, x2, xn, they are simply indicating some numerical values, or they may be some characteristic values also. For example, we have taken earlier data set in which we have found the gender of 10 persons, and that was indicated as say male and female, and that was categorized by 1 and 2 also. So, these are some values. Okay. So, now here I am going to denote by this vector x the data vector. So, whatever data I have collected, whatever the values I have collected, they are contained in this data vector x. Now, first we try to talk about arithmetic mean. Arithmetic mean is simply sum of all the values divided by total number of observations, and this can be directly computed in the R software using the command mean of x, that is MEAN, and inside the argument you have to write the data vector. So, you do not need to write a program to compute this quantity. That means where you have to first find out the sum and then you have to divide it by the number of observations. R has already developed this program. They have compiled all the program inside a function called as mean. So, by using the function mean, I can directly compute the arithmetic mean. So, now next measure we are going to consider is the geometric mean. We all know that this is defined as the product of all the observations and then we try to take its nth root. This is how we compute the geometric mean of the data x1, x2, xn. In R package, there is no direct function to compute the geometric mean, just like arithmetic mean. So, what I want to show you here, that this can be computed directly using some other functions. So, for example, if you try to see here, this is the syntax of the geometric mean. First, I am going to compute the product. We had learnt in the earlier lecture that this product of x1, x2, xn, that is x1 into x2 into x3 up to xn, this can be obtained by the function PROD, that is the short form of product. So, this part of the syntax is going to give us the product, which is this one. And then this hat, as we know, that is going to indicate the power, that means the raised to the power of something. And then I am writing here 1 upon length of x. We know that length of a vector is given by length of x. So, this is going to be simply the total number of observations. What is here n? So, in case if I try to take its power by using the symbol hat, then inside the bracket I try to use here 1 upon length of x, which is denoting this quantity, right. So, this is how one can compute the geometric mean. So, now we are going to consider the harmonic mean. We all know that the harmonic mean is computed by this expression, and here you can see what is really happening. First of all, I am trying to find out the inverse of each and every observation xi, and then I am trying to find out its mean, right, and after this I am going to find out its inverse. So, there is no direct formula to compute the harmonic mean, or there is no direct function to compute the harmonic mean in R. So, what we try to do, we use the mean function and we try to devise the syntax for computing the harmonic mean. So, what we try to do here, this becomes simply 1 upon mean of 1 by x. So, this is how one can compute the harmonic mean in the R software. Next we try to consider another popular measure of central tendency, which is median. We all know that median is the value which divides the entire frequency or the total frequency into two equal parts. So, this is a value such that the number of observation above it and the number of observation below it, they are the same, they are equal. And in order to compute the median, we have a direct function in R, and the syntax of this function is median, and inside the argument this is the data vector. So, you simply have to write MEDIAN, already small letters, and inside the argument you have to simply give the data vector. So, after having these simple functions, why not to implement them over a small data set and see what really happening. So, now here we consider a data set of 15 observations, and all these values are combined in a vector here C, and these numbers are representing the marks of some students. So, I call it a vector marks and I try to store it in R. So, you can see here is a screenshot of this vector. Then in order to find out the mean, that is arithmetic mean, we simply try to use the command MEA and mean, and inside the argument the data vector. So, this is here marks. So, you can see here is the value 63.2. And similarly, in order to compute the geometric mean, I try to use the same command, that product of marks and then raised to the power 1 upon length of marks, and then I get here this value, and here is the screenshot of the outcome. Next we compute the harmonic mean, and you can see here this is the syntax. Marks is my data vector, and I try to do here 1 upon mean of 1 upon marks, and I get this value over here, and here is the screenshot of the outcome. And similarly, if I want to find out the median of my data marks, then this is MEDIAN median, and inside the argument this is the data vector marks, and I directly get this value 63, and here is the screenshot. But why not to do this thing over the R consoles and try to see what do we obtain. So, first let me try to create here the data vector, and you can see here this is here marks. And now if I want to find out the mean of marks, then this is 63.2, and similarly if I want to find out the geometric mean, then this is given by the syntax like this, and if I want to find out the harmonic mean, this is given by the syntax this, which is 55.78, and now if I try to find out the median of this marks, then this is given by the same command median of marks, and this is 63. So, you can see that it is not difficult to compute these measures, and similarly on these lines you can compute other measures also, which are available in the as a built-in function in the base package of R. So, now we come back to our slide and we move further. Now, in this slide I want to show you an example which many people commonly make. The issue is this: whenever I want to find out the mean, I have to give the value in the format of C, that is a vector, using the command C. But suppose if I simply want to find out mean of 1, 2, 3, 4, then still you will get an answer 1. But the mean of 1, 2, 3, 4 is not 1, because this is 1 plus 2 plus 3 plus 4 divided by 4. So, the reason is that when you are not using here the C command combined function, then it is only considered the first element, and it is trying to find out the mean of only the first element, that is 1 upon 1, which is equal to here 1, right. And the proper way to find out the mean of 1, 2, 3, 4 is that please try to write down all the values inside the vector by using command C, and then you try to find out the mean, you will get the correct value. and here are the screenshots, so you can try it yourself. Now we move to another aspect. We have talked about mean. Now there is another aspect in the data analysis that is called as variability. What is this variability? First we need to understand. So now if you try to see in this slide, I have created a small picture. This picture is actually having two colors of dots. One is here something like green color dots like this one, and another are red color dot. And this green color dot and red color dot, they are representing some data. So what's really happening that I have got here two data sets. Set number 1 is suppose represented by green dots, means I have plotted it, and set number 2 values are denoted by red dots. So now when I try to plot it, what do you observe here? You can see here that the measure of central tendency of green dot and red dot, that is somewhere here. But the values which are denoted by green dots, they are concentrated only in this area, and the values presented in the red dots, they are concentrated in this area. So now if you try to find out the mean of both the data sets, possibly they come out to be the same, but they have another property that the values in the green and red data set, they are scattered around the mean, which is here like this, a big green dot, but their scatteredness is more. For example, all the values in the green dot, they are scattered only inside this circle, whereas the values in the red dots, they are contained in this bigger circle. So this is the property which is called as scatteredness, and this is the property which is called as scatteredness of the data, and we would like to quantify it. And in order to quantify it, we have different types of function, and by those functions we try to measure the variability, right. So now I try to take some values in the two data sets. Suppose this is my data set 1 having 3 values 360, 370, 380, and second data set having 3 values 10, 100 and 1000. You can see here when I try to find out the mean of these 3 values and mean of these 3 values, this comes out to be the same 370. So now my question is how do I differentiate between the two data sets? They have some properties which I want to quantify, and this is about the variability of the data. You can see here that 360, 370 and 380, they are very close in comparison to the 3 value 10, 100 and 1000. So that is a property which we try to measure with the different measures of dispersion, and there are different measures of dispersion that we talked about: variance, standard deviation, mean deviation, range, interquartile range and so on. So now we are going to discuss those measures one by one, and we would also like to see what are the different syntax or functions available in R package. Okay. First quantity I am going to discuss is variance. The variance of a data set here x means, again I have got here value x1, x2, xn. The variance of these values x1, x2, xn is defined by this 1 upon n summation I goes from 1 to n xi minus x bar whole square. So it is simply trying to say take each value x1, x2, xn, then try to find out the difference from their arithmetic mean, and then try to square them, then try to take the average of these squared values, and this function is called as variance. So in R, this variance can be computed directly by the built-in function VAR, and the syntax is VAR, then inside the argument we have to give the data vector. And when I try to take the positive square root of this variance, This is called as standard deviation. In some places they talk about standard error also. Standard error and standard deviation have some differences from the conceptual point of view. Yeah, but here I am not going into those details, but from the layman language I would say that okay, you try to treat standard error and standard deviation in a simple way. They are more or less like the same thing for us at this moment, but definitely I would repeat, there is a difference, they are not the same. In order to compute the standard deviation, we simply have to take the square root of the variance of x, and the syntax is like this: SQRT and then square root of VAR and then the x data vector. So, it is as simple as that, finding out the square root of variance whatever you have found. One thing which we have to be cautious, that in statistics there is another variant of variance, and in this variant the divisor here is 1 upon n minus 1, whereas in the earlier case this was 1 upon n, I goes from 1 to n xi minus x bar whole square. So, in many situations we want to use this format. So, this format if you want, then you simply have to multiply the variance of x by n minus 1 upon n. Why? If you try to see here, if I say this is my here, say here V1 and this is here V2, then I know that summation xi minus x bar whole square, I goes from 1 to n, this is equal to here n minus 1 times V1, and this is same as n times V2. Right. So, this transformation n minus 1 times V1 is equal to n times V2 is used, and we simply obtain that in case if I am trying to find out the variance of x, then this has to be multiplied only by a factor n minus 1 upon n. This is the length of x vector, which is the total number of observation available in the x vector. So, this is how I can also compute this variant, and we have to be careful whenever we are using a software, and we have to ascertain that which of the form the software is using. Similarly, there is another variant what is called as range. The range is defined as the difference of maximum value of the data and the minimum value among the data set. That means I simply have to take the observation and then I have to find which is the largest observation and which is the smallest observation, and then I have to find their difference. So, this range can be very easily computed by using the built-in function max and min. So, max gives the maximum among the values which are contained in the data vector x, and min gives the minimum value that is contained in the data vector x. So, this difference maximum of x minus minimum of x, this is going to give us the value of the range for the data vector here x. Right. The next popular measure is interquartile range. The interquartile range is simply defined as the difference of third quartile and first quartile. We had discussed in the earlier lecture what are quartiles, means the entire frequency is divided into 4 equal parts. First quartile, second quartile, third quartile, fourth quartile, second quartile is the median. So, I try to take the difference of third quartile minus first quartile, and this quantity can be directly computed in the R using the function IQR, which means interquartile range of the data vector x. Next measure is quartile deviation. This quartile deviation is another variant of interquartile range in the sense that it is defined as the difference of third quartile of the data minus first quartile of the data divided by 2. So, this is essentially the half of the interquartile range. So, there is no need to have a separate function for computing the quartile deviation. Once we have a function for computing the interquartile range, I simply have to make it half. So, the syntax to compute the quartile deviation is simply IQR, which is interquartile range of the data vector x divided by 2. So, that is pretty simple and straightforward. Similarly, the mean deviation is defined as the average of the absolute deviation from the arithmetic mean. X bar here is this here mean, and what we are trying to do, we are trying to take every observation, say ith observation, and I would like to take its deviation from the arithmetic mean, and instead of squaring it, I will try to take its absolute value, and then I will try to find out the arithmetic mean of all the absolute values. This is called as mean deviation, and this mean deviation is least when it is measured around median. But here we are trying to compute it from their x bar. There is no direct function to estimate the mean deviation, but we have to just use the built-in function, and then we have to write down the syntax for computing the mean deviation. So, now if you try to look at this structure, it is pretty simple. We know how to compute the arithmetic mean, that is mean of x, and we also know how to compute the absolute value, the function is ABS, and we also know what is here n, this is length of x, and then we also know how to find out the sum. So, I simply have to write the syntax here, sum of absolute value of x minus mean of x. Just be careful about the number of arguments, means left hand side and right hand side argument should be matching, and divided by the length of x, and this is how I can directly compute the mean deviation using the built-in functions. Okay. So, now we considered an example here. This is the same data set which we had used in the earlier example, where I had collected the observations on marks of 15 students, and they are combined inside a vector marks. So, I try to expose all these functions whatever we have done on this data set marks. So, in case if I want to find out the variance of marks, I simply have to write down VAR, inside the argument I have to write marks, and as soon as you enter you get this value. And similarly, if you want to find out the standard deviation, you simply have to take the square root of this value mark, and as soon as you operate this function you get here the value 20.95, and here the screenshot of the operation. Now, we compute the interquartile range. So, we know that the function for the interquartile range is simply IQR in capital letters, and the data vector here marks, and as soon as you enter it you get here the value 33. And similarly, if you want to compute the quartile deviation, you simply have to divide the interquartile range which you have obtained here by 2, and you get here this value 16.5. And in case if you want to compute the mean deviation, you simply have to use this expression, which is simply 1 upon n, summation I goes from 1 to n, absolute value of xi minus x bar, and this gives us this value, and here are the screenshots. So, why not to do all these things on the R console and try to see what do we obtain. Now, we come to our R console and try to do all these things over here. So, you can see here we already have this marks data set. So, now first I try to find out the variance of marks. You can see here you have to use the function VAR. As soon as you enter you get its variance, and in case if you want to find out the standard deviation, you simply have to find out the square root of variance of marks, and the positive square root is called as standard deviation. So, this is the standard deviation of the data vector mark, and now if you want to find out the interquartile range, so you simply have to type IQR and the data vector here marks, this gives here 33, and similarly if you want to find out the quartile deviation, which is the half of the interquartile range, so you simply have to write down IQR marks and divided by 2, this gives here this thing. And in case if you want to find out the mean deviation, this is here given by this thing, and then you can see here this is given by like this, value 17.41. So you can see that it's not very difficult to compute these values directly from the R software. So now let us come back to our slides and try to see what we can do more. Now we try to consider the earlier example where I had considered two data set 1 and data set 2. Data set 1 has value 360, 370, 380 which are very close, and data set 2 has value 10, 100 and 1000 which are quite far away from each other. And then I try to find out the mean of data set 1, this comes out to be 370, and the mean of data set 2, this comes out to be 370, and both these values are same. Then the question was, what is the difference between the two data set, or how to discriminate between the two data set. So now we know, we simply want to compute the variability. For example, we try to compute the variance of data set 1, this comes out to be 100, and then I try to compute the variance of data set 2. This comes out to be 299700, which you can see here, this is much larger than the variance of data set 1. So obviously now you know that there is another feature which is contained inside the data set, which is given by the variance, and now you have quantified it. So you can choose a data set which has got the lower variance, that is always preferred. Now a word of caution. Suppose you want to find out the variance of 4 values 1, 2, 3 and 4, and suppose you use the variance function VAR directly on these values 1, 2, 3, 4 which are say given inside a argument, then you will not get anything, but it will give you that there is some problem in this command, and this is an invalid command. Why? Because you have not given the values in the form of a vector. So in order to find out the variance of 1, 2, 3, 4, first we should combine them in a vector using the C command, and then use the variance function, and this will give us the correct value. And here are the screenshots of the outcome, so you can see and you can try yourself. Now we stop in this lecture, and we have learned how to measure the central tendency of the data and how to measure the variation in the data using some popular functions. And you need not to write a individual program to write down these quantities, but our base function is giving all these functions directly. They are the built-in functions, and that is the advantage of using R, that you can compute all these values directly without any trouble. So I would request you that you please try to do some practice using some data sets, and we will see you in the next lecture with some more topics. Till then, goodbye.